Let's talk about work energy theorem. Work energy theorem states that the net work done by all forces acting on an object is equal to its change in kinetic energy. So what does that mean? Picture a box, all right? Either it has friction or it doesn't have friction, your choice. Let's say I pushed or pulled the object. Your choice as well, if you want to push or pull this object. Let's express this box as a mass in units kilogram. I like SI units. Okay. So, it has moved. I applied force into this object and it will move. Let's just say that this mass is very uh, movable. Let's just say that this mass is something that I can push. Because sometimes there are very heavy masses that even for someone like me, I can't push it. So therefore, there will be no work, right? So if I pull or push this object and it moves by a certain distance called displacement, that is work. I just did work on the box. I just did work on this entire box. Because it moved, I applied force in it, and then the object moved in the direction of my force. And that is work. But notice this. Isn't the definition of kinetic energy isn't the definition of kinetic energy a energy that is possessed by a moving object? Energy of a moving object. The energy of a moving object. And since work is also a transfer of energy, I am transferring energy to this object in order to move. So I can put work in it. I'm putting work on this object and it moves. And that movement, during that movement, it has energy. And what is that energy? Kinetic energy. But of course, since I just applied a few force, eventually the friction will make it stop. So there's a change in that kinetic energy. And that is the intuitive idea behind the work energy theorem. W is equals to delta KE. Or, much better, without using the letters KE, work is equals to delta T. So how do we derive it? Simple. We just use this formula, FD. The simple definition for work. The simple mathematical definition for work. And then we will use Newton's second law of motion. Mass times acceleration is equals to force. Now we will use that into our formula. Let's go ahead and plug that in. So we have ma times d. Now, do you guys remember this third kinematic equation of motion, which is v of f squared is equals to v sub o squared plus 2ad. This is the third kinematic equation of motion. This one is the initial velocity, and this one is the final velocity. So let's solve for AD. So now let's remove the parentheses. So we have MAD. Mad. Work is mad, apparently. Now let's go ahead and solve for AD. Minus both sides of the equation by V sub O squared. So now we have this. Divide both sides of the equation by 2, and we get an expression for AD. Now, we will go ahead and substitute this to our expression for AD. So now we have work equals mass times V sub F squared minus V sub O squared all over 2. Using distributive property, we will go ahead and distribute mass to both expressions, both terms of the numerator. So we have mass times V of F squared minus mass times the initial velocity squared all over 2. Now we can go ahead and split this into 2 fractions. And now we have mass times the final velocity squared all over 2 minus mass times the initial velocity squared all over 2. And notice this expression right here. Isn't kinetic energy defined as 1/2 mv squared? And it matches the exact same definition here. So, therefore, this is actually the final kinetic energy minus the initial kinetic energy. And that is exactly the mathematical definition for the change in kinetic energy. So we have derived the work energy theorem. And that is work equals delta